These notes are about how we would solve logarithmic equations. We're going to have log functions involved, so our variable might be next to the word log. We might see a variable involved with logarithms. We have a very important fact that we need to be comfortable with before we begin. We need to know the fact that log base b of x equals a can be rewritten in exponential form, b to the a equals x. They mean the same thing, we're just writing them in different forms. You'll see in our notes today, we're going to be starting with things that have logs in them. We're going to be starting with log form. And you'll see that if we're comfortable with rewriting those in exponential form, then we'll be able to solve for x. Notice this form has x solved for. X equals b to the a. Let's take a look at our first kind of straightforward example in green. Log of x equals 2. Solve for x. Well, we know that our base is 10. It's not written in, but it's our common logarithm. If I write this in exponential form, that becomes 10 to the 2 equals x. And our solution just kind of fell right out of it. Rewriting it in exponential form allowed us to solve for x really easily. 10 squared is 100, x is 100. That makes sense. Of course, log of 100 equals 2. That was a very basic example. Let's take a look at this example. Still pretty basic, but now instead of just log base 2 of x, we have log base 2 of 3x minus 2 equals 3. We can rewrite this in exponential form as 2 cubed equals 3x minus 2. This whole 3x minus 2, that binomial, is kind of in the place of where x was in the previous example. We still treat it as one sort of chunk. 2 cubed is 8. And now it becomes a very simple linear equation. I can add 2 to both sides and divide by 3. So x here is equal to 10 thirds. The last thing you probably want to do is check your solution. And here I can even just do a visual check. If I plug in 10 thirds for x, I would get 3 times 10 thirds minus 2, which would be 8. And yeah, log base 2 of 8 is 3. That does make sense. You have to be careful because you might encounter some extraneous solutions. I know that if I had a log of x expression, I would know that x would have to be greater than 0. So we just want to be careful of things like that. Take a look at this example. We're getting a little bit more complicated here. So far, our strategy has been to rewrite our log equations in exponential form, but we can't do that here. We can't do it yet because we have 2 separate expressions that have the word log in them, so I can't go immediately to exponential form. Luckily, we have some log properties that we've learned about that allow us to rewrite the sum of 2 logs as the log of a product. Log base 2 of 3 times x plus 1 is equal to 4. I used the product property of logs. And actually, I can simplify what's in the parentheses. Log base 2 of 3x plus 3. Notice I distributed that 3. Now it looks very similar to the previous example. I can go to exponential form. 2 to the 4th equals 3x plus 3, and it's become a linear equation again. 16 equals 3x plus 3. So 3x is equal to 13, and x is equal to 13 thirds. I just want to make sure that that makes sense as a solution. And yeah, if I plugged in 13 thirds for x, 13 thirds plus 1 is definitely positive. It seems to make sense. Doesn't look like a solution that I wouldn't be able to plug in and check. This example is again similar, but now I have a difference of logs. And again, we can't go right to exponential form because we have 2 separate log expressions. But again, we can use those log properties we've learned about to combine them into a single log expression. It is the difference of 2 logs. I can rewrite that as the log of a quotient. So there's a real reason that we spent so long on log properties beforehand, because they're coming in handy quite frequently when we're solving. So all I did is I rewrote that as a log of a quotient, and I can actually do some canceling in that fraction. I see an x and an x squared in the bottom. So I can cancel that into 1 over x. I can rewrite this as log of 5 over x. I canceled an x in the top and the bottom. Now I have to be careful because anytime I'm canceling, I might have ruined a solution. I might have lost a solution. So the only time that's not really allowed is if x was equal to 0. I might have lost the solution that x was equal to 0. But if you look back, x equals 0 can't possibly be a solution, because then I would have log of 5 times 0. So I actually don't have to worry about canceling my x's, because x equals 0 wasn't even a solution. So it's important to think about that. If you're canceling a variable, you might have lost a solution, but in this case, we didn't. Now I can write this blue equation in exponential form. It's the common logarithm, since our base is not written in. 10 to the 1 equals 5 over x. We can now maybe solve this. Maybe it's a little bit easier to see if we write 10 over 1. We can cross multiply, or we can multiply both sides by x, however you want to think about it. That turns into 10x equals 5. So x is equal to 5 over 10. Or I'm going to write that as x is equal to 1/2. Not so bad, just using our log properties. Let's do one last example. We haven't seen natural log in a while, so let's bring it back and see what could possibly happen here. Natural log of x plus natural log of 2x equals 3. I know I can use my log properties and write this as the log of a product instead of the sum of two logs. And now I have x times 2x after natural log. Well, what is x times 2x? That's 2x squared equals 3. So now we'll have to be careful because it looks like I'm going to end up with a quadratic equation, which tells me there might be two solutions here. I'm not too sure. Well, let's see what happens. When we go to exponential form, we have to be careful because our base is e. Natural log means log base e. When we go to exponential form, that looks like e cubed equals 2x squared. Now I could take out my calculator now and calculate e cubed, but then I'll be rounding very early on in the problem. So I'm going to actually solve for x and save my calculations till the very, very end, the calculator calculations, that is. We'll divide both sides by 2 to get x by itself. And we get that x squared equals e cubed over 2. Again, that's just going to be some decimal. I'll worry about what that decimal is a little bit later on. And now if x squared equals a number, to get x by itself, I'd want to square root both sides. But there is going to be a positive and a negative solution algebraically here. If a number squared equals e cubed over 2, there could have been a positive or negative value for x. So our two solutions are x equals the square root of e cubed over 2, and x equals the negative square root of e cubed over 2. Now I might take out my calculator and say, what is e cubed over 2? I have my e key on the calculator. So what I'm doing is e cubed divided by 2, and then I'm going to take the square root of that value. And I get that that's about 3.169. And in this case, it would be about negative 3.169. Now the question is, do both of these solutions make sense here? If we try to plug in our negative solution, we'll realize that it actually doesn't make sense here. Natural log of x is the first term I see in our equation. If I plug in negative 3.169, I have natural log of negative 3.169, which wouldn't make sense if I tried to check it. That tells me that this is an extraneous solution. We have to be careful because sometimes there will be two solutions that work. But in this case, they're not. This one does work. This is our exact answer. If I just leave it as root e cubed over 2, which is fine. If I wanted to approximate that with the help of my calculator, I would write that as 3.169. So our general strategy for solving log equations is to make sure you get your equation in the form that's able to be rewritten into exponential form, and that will help us solve. Sometimes we'll have to use log properties, sometimes other ideas to try to isolate the logarithm, but we'll always be able to solve for x in examples like these. It's just going to require comfort with switching from log to exponential form. Good luck!